Hello, so my name is Duncan Poole, and I'm responsible for the platform alliances at NVIDIA. Well, what does that mean? Platform alliances means that set of alliances that relates to deploying HPC infrastructure. So compilers, profilers, debuggers, the MPI stack, relationships with the Linux vendors as well, all designed to put together the framework. What I'm going to try and do today is pay respect to all the unnatural acts that people have had to do over the years to port to NVIDIA GPUs. The two quotables I think I've heard so far at the show that I like the most, one is that nobody wants to go parallel. They need to go parallel. And so with it comes all the pain of going parallel. And the other one was from a scientist who said, you know, the science I can do is limited by the amount of programming I can get done before I die. And so my hat's off to the people that take the time to port to these things. So what I'll do is I'll flip through some rather pretty slides with the intent of poking at where the work was. And we'll see where that goes in conversation, okay? So we announced at this show, or the DOE announced at this show that the #1 spot was once again regained by an NVIDIA-based system. And this is Summit over at Oak Ridge Labs. World's fastest supercomputer, one that's enabled with 28,000 tensor cores, which is our special sauce that was added to the Coral work environment to allow for doing math, the reduced precision math that's associated with doing deep learning. 3 exaops. What's an exaop? 3 reduced precision operations being able to be performed in this kind of machine. So, so where was the work? This is the first machine that ever used NVLink to a motherboard so that you could actually have address translation operating between a host and a GPU. You know, malloc, a pointer is just a pointer on this machine. So a very interesting innovation here. Obviously, it's not the only machine that we have that's like this out there now. Sierra was also announced, the other Coral machine. Japan's purpose-built AI supercomputer that is a Univa customer as well. PISDINT, which is the top machine in Europe. So I guess we have Japan and Europe and North America. And I actually don't know what, in Australia, there's POSI, which may be the largest supercomputer in Australia as well. So we're doing pretty good with continental drift. And then finally, we have some industrial use cases that are creeping forward here as well. In terms of application growth, I think what has made NVIDIA successful has really been the capturing of the developer mindset. So this is, for us, measured by looking at the CUDA compiler and the CUDA development environment, and you know, how many downloads do we have now and this year compared to years before. So this is this measure of 1 million to 8 million CUDA downloads so far this year. In the case of actual applications, we also have a tracker for this. But when you put it all together and look at the broader work that had to be accomplished here, now the platform gets much more interesting. You know, we have at the lowest level GPUs that have been built for appliances. This is the DGX family that have been built for systems integrators. So this is HGX and our fanless GPUs. And then finally, with our cloud providers, you know, there's been a grand proliferation of that same capability into the cloud. And you know, with deference to the prior speaker, you know, one of the benefits that's about what's being deployed now is these very dense nodes, because you can get a high degree of scaling within a single node when you have, you know, 4 to 8 GPUs within the node. Each GPU is, I think, if you want to keep one GPU fed, it's about 150,000 threads of work at any one time. So the parallelization effort that's involved here is kind of substantial. So from the standpoint of a pictograph that describes what that form factor is, this is what you see now. So Titan and Quadro, which is the classic workstation. What you might note here is that this one's got a fan. It's still got NVLink, but it's got a fan. And if I'm a systems management provider, this myriad of quick innovation from NVIDIA, different classes of GPUs, fans, no fans, it all results in kind of a maintenance nightmare if you don't know how to provision a given load to a given environment. And you see in the data center here we have small form factor GPUs, still based on Volta, but they're designed to be powered by the PCI Express bus versus the ones that might require external power and cooling. That's quite special. And then of course with CUDA, you see NVIDIA reaching into the automotive space, and I would point out there's some interesting challenges because you could do sensors within the car where you do compression at the sensor, or you could deploy a very high-speed network bus that allows the fundamental raw sensor data to be sent back to the processing core, and then at that point do the reductions. So there's some choices that are going on here that are interesting in the field. Again, all programmed with CUDA, this time based on ARM, so it's a little different, if you like, from the standard one. And then every variant under the sun. We'll build these appliances that are kind of reference architectures, and then from the various vendors working with the cluster management partners is how these new machines are getting built up. And this gives you some sense of what the GPU choice was made and what the form factor ultimately looked like. So there's quite the set of innovation that happens after it leaves NVIDIA's hands. And speeds and feeds that relate to this. At this point, we have NVLink support. I've got a better graphic of what this looks like in a slide, so you'll have to give me a second on this. But again, available from all the OEMs you might expect, and then several that you would not, like such as Cisco and some of the ones overseas. I mention these again primarily because they are they're unique in their scaling, in the challenges they're trying to address with respect to scaling. So with this most recent release of NVLink-enabled GPUs, we now also supply something called NVSWITCH. And so the switch is the ability to do 16-way GPU with a common memory address space between them, and the ability to fork jobs from one GPU to the collection of GPUs. If I think about how, we talk about affinity between running a task, how close it is to the CPU, how close it is to another GPU with a strong network like this. We're presenting challenges to the cluster management vendors about how to describe this for job submission that hasn't been seen before on NVIDIA. So hats off to them for this. And you get some sense of the speeds here. I'm not going to read the speeds, they're on the slide. A little more detail about how this thing all fits together. So with NVSWITCH, we deploy effectively a 2-fat node rack inside a box with, you probably have a better slide than this. Let me just get to this slide. With, here we have InfiniBand EDR attaching these 2 fat nodes with special purpose cooling, with highest end Intel processors we can find, with, NVMe storage. It's a study in a box for what you could scale to if you wanted to. So, and our CEO calls it a single GPU more because of the programming paradigm that's associated with it. So, in terms of overall performance, we can do some somewhat apples-to-apples comparison between our earlier appliance, which had no NVSWITCH, and this one, and you start to see the HPC capabilities that are available within that environment. And to my mind, what's interesting is not that we've made this box, it's what the vendors will do with this box next. And what does it mean to support an ecosystem of apps that are able to run, getting ahead of myself, as containers on this environment or, on their other machines. And so this is the form factor, HGX, that we use that's designed to be carried out by those vendors to be used in the cloud or in denser node configurations. Okay. That was hardware. For software, most recently, the effort has been to move to a cloud-based model, containers-based, work with all of the various scientists that are porting their applications, ANSYS, Fluent, Gaussian, GROMACS, NAMD, Amber, and create containerized versions of their software that can then be, because it's containerized, simply deployed with all the dependencies resolved. And so with NVIDIA, if you're a member of the NGC, you can download these and run them on any desktop Volta. You can run them on your AWS instance. You can run them on your server. So the idea is to simplify this kind of work. So, and as usual, I get ahead of myself. This is kind of the justification for that. Create the federated, resolved dependencies and know that you didn't have to build up from scratch your version of that app. This gives you some sense of the set of apps. So the HPC space is slowly building out. Obviously we started with the deep learning space because that was interesting in its own right. So deep learning, I think, was successful with us because we were building a set of base level libraries for DNNs and other operations. Libraries allow relatively quick deployment, relatively quick adoption. It's harder to use programming languages to move applications forward. So by supplying these base level libraries, this is what I think has fueled it. And again, hats off to the cloud providers because you don't have to have bought one of these things to actually do this development and get moving in the cloud. So with CUDA, with the latest release, we have support for our tensor cores. We have support for these cooperative groups that let you use NVLink if you have it or NVSWITCH if you have it to deploy or to create groups of cooperating processes. Getting ahead of, on NVIDIA, we have hardware scheduling for threads. So depending upon the topology, these cores can be leveraged. We also have, to my chagrin sometimes, we have thermal throttling, which is something that a cluster vendor can turn on or off. That you turn it off because you want to get the best performance possible. You turn it on when some scientist comes to you and asks why, for some reason, some of his nodes finished 15 minutes earlier compared to others. So it's sort of an interesting problem. And then the extension to this problem with CUDA is that, of course, we supply support for Mac, for Windows, for Linux in its various flavors, and it all results in a need to, how do you manage all these possible variants unless you're working well with your cluster management partners? And the host compiler list on the right are the compilers that either have direct support for GPUs or the callable as a host component for the host operations. One of the things that we do is OpenACC, and so this is just the set of apps that we were porting most recently in this area. I'm not going to go into it now, but it's an attempt to make programming a little bit simpler. And then finally, I'll finish with this slide, which is what do we do directly here with Univa, and that's really create a set of management libraries that allow people to look at the health of the system and do policy management about how some of these jobs are deployed, and work with us to create a framework for application deployment. So we create the APIs, and then Univa has to put them into their framework and make them available. And so, I want to thank Univa for doing that, of course. But that's the nature of the challenge that surfaces here. So with that, I'll stop and take any questions that you might have right now.